Hi, I'm Amanda, and I'll be discussing how to leverage administrative data for audits of demographic bias in the context of mobility data for COVID-19 policymaking. This is joint work with Neil, Lisa, Derek, Alex, and Dan. Large datasets offer the potential to gain new insights and may be an important problem-solving tool, particularly in rapidly unfolding crises like the COVID-19 pandemic. Of course, we know from a large body of work, including from this community, that big data often has significant demographic biases, so it is important that we interrogate these datasets for bias. A key challenge is that we often don't have access to the sensitive or protected demographic attributes in our data. And another challenge is that we often don't have ground truth outcome data. We show how to use administrative data to overcome these challenges and facilitate audits for demographic bias. We do so in the context of smartphone-based location data, which I'll call mobility data. Mobility data informs the movements of millions of people across the US. Understanding where people are and how they move is important for effective policymaking during a pandemic. Many government bodies are using this data to inform public health orders and guidelines. And given this high-stakes setting, we need to understand biases and inaccuracies in this data. This is particularly challenging because mobility data does not contain demographic information, and we don't have ground truth data. We emphasize this point because a large body of work from machine learning researchers and epidemiologists use mobility data as if it were ground truth, and sometimes even describe the data that way in publications. But much like other settings, for instance, criminal justice, where rearrests are only a noisy proxy for recidivism, here too, our data can lead us astray. For instance, smartphone data may suggest someone is at the Golf Galaxy, when in fact they are visiting the nearby Walmart. An error in the device localization could cause this, or perhaps the data company has the wrong building geometry. This became an issue early in the pandemic when the San Jose Emergency Operations Center wanted to identify non-essential businesses that weren't complying with the lockdown. The golf store seemed to be getting thousands of visits a day, even though it was supposed to be closed. But to their credit, before sending police, the center realized this was likely a misattribution problem that did not warrant investigation. But this isn't the only issue. We should also be concerned about potential demographic bias. Smartphone ownership rates vary significantly with age. In 2019, nearly all those aged 18 to 29 had a smartphone, whereas only half of those aged over 65 did. We might then suspect that people over age 65 are underrepresented in smartphone-based mobility data. We don't really see differences in ownership by race, but usage might still differ in a way that matters. To understand this, let's dive into the data. We are using data from FAccT, a company that provides traffic estimates for 6 million places of interest called POIs, which is anywhere people spend time or money, such as schools, restaurants, shopping centers, airports. The company aggregates traffic from 47 million devices obtained via opt-in location sharing on mobile apps, including weather, navigation, social media. If there are demographic differences in who uses these apps or who allows location sharing, then we will have sampling bias with respect to demographics. Specifically, we are interested in whether FAccT has sampling bias with respect to age or race. We chose these demographics in particular because they are risk factors for COVID-19 related mortality. The challenge in answering this question is representative of a wide range of settings where we want to assess demographic bias but lack access to the protected attribute and to ground truth outcomes. The only prior bias assessment was from FAccT itself. They use census block groups, which are geographic areas containing typically between 600 and 3,000 residents. For instance, here is the CBG that includes most of Carnegie Mellon University. This analysis assigns each FAccT device to a home CBG based on where the device spends most of its nights, and they use the CBG demographics to infer the device demographics. For example, consider a CBG with 200 residents, half of whom are white, and a quarter who are Asian, and a quarter Black. If FAccT has 40 devices assigned to this home CBG, For their assessment, they will consider this to be 10 Black, 10 Asian, and 20 white devices. They then compared the census count on the x-axis to the device counts on the y-axis for each race. And since the points are close to the y equals x line, they concluded they have a representative sample. And to their great credit, SafeGraph made this assessment publicly available and noted themselves that there are limitations to this analysis. First, it's not clear what this design is testing. The analysis seems to be looking at variation across CBGs by race, but assumes that within a CBG, you have proportional representation by race. Secondly, outliers could wash out any true variation using this aggregation scheme. And finally, because they don't have access to demographic attributes, they rely on CBG attribution to estimate demographics. But CBG attribution can be quite inaccurate. For instance, CBGs containing airports have many more devices than people who actually live in that CBG because you have a lot of nighttime workers at the airport whose home CBG is incorrectly assigned. So given these limitations, how could we conduct a more rigorous bias assessment? Ideally, we would want to see whether coverage or representation varies with demographics. For illustration, I'll use age, letting orange denote older individuals and black younger individuals. Solid figures are measured by SafeGraph and the hollow figures are missed. Here, the coverage of older individuals is 1 in 4, whereas for younger, it's 100%. However, because the data is aggregated for privacy reasons, we can't evaluate this, but we can evaluate coverage at the POI level. Imagine that each box here is a different POI, like a store or place of worship. In this hypothetical example, the first POI has the oldest population and worst coverage, and the bottom row has the youngest population and best coverage. If we see such a trend in the data, we may conclude there is disparate coverage with respect to age at the POI level of aggregation. To test whether such disparate coverage exists, we can test the null hypothesis that the rank correlation is 0 between POI coverage and age distribution of the POI visitors. This setup resolves a couple issues with the prior analysis. We have a clearly defined test that is robust to outliers. However, in order to do this, we need ground truth demographics. This is a tall order because it's already hard enough to get daily traffic to POIs, which is why many researchers use SafeGraph as if it were ground truth. But we need a much finer grained picture. We need to know the age and race of each visitor to a POI on a given day. So we consider large-scale events like sports games or concerts where you can get independent estimates of the daily traffic by turnstile data, but how would we know the demographics of each visitor to, say, a Seahawks game or a Chiefs game? Well, fortunately, we realize there is one event for which demographic information is available: elections. Voter turnout data gives us individual information for every voter, such as whether they voted in a particular election, as well as their race and age. And we can figure out where they voted by their precinct and county information. This is great because we now have individual demographic information for every voter, but there is one problem. Not everyone who visits a poll location like Saddle Tree Community Center on election day is a voter. There could be a trivia night or arts class at the community center. And this could be a problem if this non-voter traffic varies with voter demographics. For example, if older people vote at places like fire stations with little non-voter traffic, but younger people vote at places like community centers with lots of non-voter traffic, then it would be impossible to identify whether variation was due to disparities in SafeGraph coverage based on age or is due to non-voter traffic that varies with age. To address this, we use a mean imputation type approach that estimates non-voter traffic to a poll location by averaging traffic on the adjacent days. We subtract off this estimate of non-voter traffic to obtain what we call the SafeGraph marginal election traffic. Here is a plot of poll locations by the number of voters at that poll location on the y-axis, against the FAccT marginal election traffic on the x-axis. We see a positive trend, which is good, but there's a lot of noise. We then define coverage for each poll location as the ratio of FAccT marginal election traffic to the number of voters. This is our proposed procedure for estimating coverage, but we could still have confounding under this estimation procedure. What I mean by a confounder is a factor that affects voter demographics and non-voter traffic on election day. We distinguish confounders based on whether they also affect traffic on non-election days. We refer to a confounder that affects traffic only on election day as a time-varying confounder, which we differentiate from confounders that also affect traffic on non-election days. We refer to these as time-invariant confounders. For instance, time-varying confounding could occur when younger people vote at places that are open to non-voter traffic, whereas older people vote at places that are closed to non-voter traffic on election day. Time-invariant confounding occurs if, for instance, younger people are more likely to vote at places whose busiest day is Tuesday, whereas older people are more likely to vote at places that are busier on other days of the week. We have to assume no time-varying confounding for our inferences to be valid, but we do not need to assume anything about time-invariant confounding since we can build this into our test. And we can do this by modifying our null hypothesis. Previously, we wanted to test whether the rank correlation between election day coverage and voter demographics is non-zero. Now we will test whether the rank correlation between election day coverage and voter demographics is different from the rank correlation between coverage on a non-election day and voter demographics. We do this by using a 60-day period around the election, and for each day in the period, we compute the rank correlation between FAccT marginal coverage on that day and voter demographics. And then we compute the p-value of the election day correlation under this placebo distribution that we generated in the first step. I'll present results for this method in a few slides, but first we'll get a sense of the data. We use data from the 2018 general election in North Carolina. After matching with FAccT, for our analysis, we have 539,000 voters who voted at 558 poll locations. We summarize the age of voters at a poll location by the percentage of voters over age 65. Here I plot quantiles of poll locations by age. So I've grouped poll locations into 30 bins according to their proportion over age 65, and then we plot the average coverage for the bin on the y-axis. So for instance, the leftmost point is the bin containing poll locations with the lowest percentage over 65, on average about 10%, and its y-value tells us that these poll locations had on average a coverage of roughly 1.5%, which means that for every 100 voters at the poll location, FAccT would capture 1.5 voters. Coverage appears to be lower for polling locations with older voting populations. And we can apply the placebo procedure from the previous slide to validate this disparity in coverage. Here I give the results of the placebo procedure. This histogram gives the rank correlation for each day of the 60-day period. The purple shows the rank correlation between voter age and coverage on election day, and the yellow shows the rank correlation between voter age and coverage on non-election days. The purple, being farther left than the yellow, correlations indicates that the negative election day correlations are unlikely under the placebo distribution. So we can reject the null hypothesis that the rank correlations are no different on election versus non-election days, and conclude that coverage is lower for poll locations with older voters. Our paper gives similar results for race, finding that coverage is lower for poll locations with a larger fraction of non-white voters. And these disparities become more pronounced when we consider the intersection of race and age. Each cell in this heat map gives the coverage, red is lower and blue is better, for different age race quantiles. Low age quartiles, which are on the left-hand side, are young and low race quartiles towards the bottom have a larger percentage of white voters. The best coverage, 3%, is among the young white population, and the worst coverages are below 1% for the older non-white communities in the upper right-hand corner. This suggests that SafeGraph is over 3 times as likely to capture a voter at a young, largely white poll location than a voter at a location with older non-white voters. These disparities are cause for concern because this data, which is used to inform COVID-19 policy, underrepresents high-risk demographic groups. Next, we do a few simulations to illustrate how policy decisions made based on this biased data can be harmful to these high-risk populations. Let's imagine the goal is to determine where to locate pop-up testing sites, and that these sites are targeted for reducing asymptomatic transmission, so the main criteria is putting them in the most trafficked places. We can compare the rankings of poll locations in Winston-Salem by SafeGraph estimates of voters, which is the SafeGraph marginal election traffic, against the ranking by voters. Perhaps we choose the top 3 locations for test sites, and if we use SafeGraph to do this, we would choose these 3 churches in the left-hand column, whereas if we use the ground truth voters, we would choose only one of the same locations, as well as a different church and a park. And our earlier analysis would suggest that the SafeGraph ordering may be biasing these decisions away from places frequented by minority or older populations. We can compute on average how we should adjust a SafeGraph ordering based on demographics by doing a regression of voter turnout rank against SafeGraph rank, age, and race. For each percentage point increase in voters over 65, we should bump the SafeGraph ranking by about 5 positions. And for each 1.5 percentage point increase in voters who are non-white, we should bump the SafeGraph ranking by 1. We'll next look at a different kind of resource distribution where we allocate resources proportionally. As an example, let's suppose we want to distribute masks. Since masks are especially important for people who are moving a lot in crowded spaces, we distribute according to how trafficked each place is. As before, we can compare an allocation by SafeGraph traffic versus by voter traffic, and in particular, let's look at how these allocations differ by age race groups. The most notable differences are in the young white group, where the SafeGraph allocation gives 33% of masks, but the voter allocation would only give 25%, and in the older non-white group, where the SafeGraph allocation gives only 13% of the masks versus 21% of the masks according to voter allocation. Allocating the masks based on SafeGraph redirects 37% of the masks that should go to the vulnerable older non-white group, and instead gives them to the relatively lower risk young white group. To recap, we have seen that SafeGraph coverage is lower for POIs visited by minorities and older populations. Due to this sampling bias, policies informed by SafeGraph could harm those already at risk. And what can we do about this? Well, an immediately feasible strategy is to use mobility data with these biases in mind. For instance, using SafeGraph to identify some highly trafficked hotspots, understanding that it will not capture all, and appropriately accounting for that blind spot. It would also be worth investigating technical solutions such as bias-correcting normalization factors. And finally, the use of administrative data was crucial in facilitating this bias audit in a setting where we lack access to the sensitive attribute. This is a pervasive challenge to conducting bias audits in many settings, and here we demonstrate how administrative data can be used to overcome this challenge. If you find yourself in a similar situation where the lack of demographic information is preventing a bias audit, we'd love to connect in the Q&A or offline. I'd like to acknowledge my amazing team and to thank SafeGraph for making their data so accessible to researchers. And thank you for listening.